You know, Alex, there's a very specific kind of quiet that descends on a shop when a man realizes he's just spent 4 hours turning an expensive sheet of 20 gauge stainless into a very shiny, very useless piece of modern art.
Is this about that custom range hood you tried to manufacture last fall? Because I remember you staring at a pile of scrap for a long time without saying a single word.
It was supposed to be a simple transitional piece, square at the bottom, round at the top. In my head, I was a master of the craft. In reality, I'd forgotten that metal doesn't just go where you want it to unless you've done the math to invite it there first. I ended up with something that looked less like a vent and more like a crumpled soda can that had lost a fight with a lawnmower.
See, that's where you always lose me. To most of us, sheet metal is just flat. Then suddenly it's a silo, or a duct, or a fender. It feels like origami with much higher stakes and sharper edges.
That is exactly what it is. We're talking about pattern development, the secret language of unrolling 3D objects back into 2D space. If you can't see the flat shape hidden inside that cylinder or cone, you're just guessing. And guessing in metalworking is an expensive way to fill up your recycling bin.
Okay, so let's break this secret language down for the people who, like me, see a funnel and just see a funnel. Where does the actual process start? Is it all just trigonometry and wishing for the best?
It starts with geometry, but honestly, it feels more like being a tailor. You're making a suit for a ghost. You've got three main ways to attack it: parallel line, radial line, and triangulation.
Suit for a ghost. I like that. So, let's start with parallel line. That sounds like the one I might actually understand without a calculator.
It's the bread and butter. If the sides of your object are parallel, like a standard round pipe or a square duct, you use this. Imagine taking a soup can, peeling the label off, and laying it flat. That rectangular label is your stretch out. But it gets tricky when you start cutting that can at an angle, like for an elbow joint. You have to project points from the side view onto your flat layout so that when you wrap it back up, those points meet to form that perfect angled curve.
And let me guess, you've projected those points to the wrong side of the sheet more than once?
I once built an entire 6-foot section of ductwork where the curve was exactly upside down. It fit the wall perfectly, but it was pointing toward the floor instead of the ceiling. I basically built a very elaborate silver trash chute by accident.
Okay, so parallel line is for things that stay the same width. What about those pointy things? The cones, the silos, the funnels?
That's where we move into radial line development. Imagine a cone. If you slid it up the side and flattened it, it wouldn't be a rectangle, it would be a big slice of pie. Everything radiates from a single center point, the apex. You have to find that true length of the side. If you use the height of the cone instead of the slant height, your funnel is going to be about 2 sizes too small, and you'll be standing there wondering why the ends don't meet.
I feel like there's a lot of true length talk in metal shops. It sounds remarkably philosophical.
It's the difference between a pro and a guy who's about to have a very bad afternoon. See, when you look at a drawing of a cone, the height you see on the paper isn't the actual distance the metal has to travel along the slope. You have to swing that length out using your dividers. It's a rhythmic thing. You're stepping off little segments around a circle to find the circumference. It's almost like a slow motion dance with a pair of pointy legs.
And then there's triangulation. That sounds like something I'd need a GPS for.
Triangulation is the break glass in case of emergency method. It's for the weird stuff. Transitions where you're going from a square base to a round top, or those off-center offset pieces that look like they've been twisted. Since you can't just unroll those, you break the whole surface down into a series of triangles. If you know the length of 3 sides of a triangle, there's only one way it can be shaped. You just keep adding triangles together until you've recreated the whole skin of the object.
So here's the skeptical question. We're living in 2025. I can see a CNC plasma cutter in the corner of your shop. Do you really need to be out here swinging dividers like a 19th century shipbuilder? Why not just plug it into a program like Calderaria Online or Fusion 360 and let the computer do the swinging?
You're not wrong. And honestly, for something complex like a Y branch or a big silo, using an online tool or dedicated software is a lifesaver. It's fast, it's accurate to the millimeter, and it accounts for material thickness, which is the silent killer of manual layouts. But if you don't understand the why behind those lines, you're just an operator, not a fabricator.
Oh, here we go. Is this the part where you tell me about the soul of the metal?
No, it's the part where I tell you that the computer doesn't know you're using a dull blade that's going to drift, or that your material has a grain that's going to fight you on a specific bend. Manual layout teaches you material allowance. When you bend a piece of metal, the inside squishes and the outside stretches. There's a neutral axis in the middle that stays the same. If you don't account for that thickness in your math, your final piece will be off by exactly one thickness of the metal for every bend. By the time you get around a square box, you're a quarter inch short.
Okay, that actually makes sense. It's like baking. You can follow the recipe on the screen, but you still need to know what the dough feels like so you know if it needs more flour.
Exactly. I've seen guys pull a perfect laser cut pattern off the table, throw it in the break to bend it, and realize they forgot to account for the deduction, the way the metal takes up space in the corner. Suddenly, their perfect part doesn't fit the frame. If they'd done a manual scratch layout once or twice, they'd have seen that mistake coming a mile away.
Speaking of scratching, I saw that in the notes. You call it scratching when you do it directly on the metal, right?
Right, if you're only making one of something, you blue the metal, put down this dark dye, and you use a scribe to mark your lines directly. But if you're making 10 of them, you make a template, a pattern,
And those are usually paper or thin gauge?
usually a thin galvanized sheet or even heavy cardstock. It's your master. You can't imagine the heartache of scratching out a complex radial development on a fresh sheet of copper, making one tiny slip with the scribe, and realizing that permanent line is now a permanent scar on your finished piece.
I'm sensing another tiger's tragedy story coming on.
It was a weather vane, a beautiful tapered copper cone. I was nearly finished with the layout, feeling very proud of myself. The cat jumped on the workbench, I flinched, and my dividers skated right across the face of the copper like a figure skater on a bender. I spent the next 3 days trying to feature that scratch by hammering it into a decorative lightning bolt.
You turned a mistake into a design choice. That's basically the definition of artistry.
It's the definition of I couldn't afford another sheet of copper.
We've talked about the flat shapes, but we haven't talked about how they actually become, 3D. The seams. That seems like where the real engineering happens.
The seams are where most beginners fall off the wagon. You can't just draw the shape, you have to draw the flaps, the edges, the joints, the laps. If you're doing a wired edge, where you wrap the metal around a stiffening wire, you have to add exactly 2.5 times the wire's diameter to your layout.
That is incredibly specific.
Metal is specific. If you give it too much, the seam is bulky and ugly. If you give it too little, it uncurls and looks like a peeling fingernail. And then there are notches. When you bend those flaps up, if you don't cut a little V out of the corner, a notch, the metal has nowhere to go. It bunches up. It's like trying to close a door with a rug caught in the hinge.
It sounds like a giant puzzle where you also have to manufacture the pieces and the glue at the same time.
And the glue is often a mechanical lock, like a Pittsburgh seam or a grooved seam. You're literally folding the metal into itself. When you see a high-end HVAC system or a custom fuel tank and those seams are tight and straight, that's not luck. That's a person who knows exactly how much meat to leave on the bone for the fold.
So, for the person listening who's looking at a sheet of metal and feeling intimidated, what's the first step? Do they buy a book? Do they download a tool? Or do they just start scratching?
I'd say start with paper. Honestly, take a cereal box, take a pair of scissors, and try to make a square to round transition. Try to see if you can calculate the stretch out of a cylinder just using a ruler. If you can make it work in cardboard, you've won half the battle. Then, go look at those online tools. Calderaria Online is fantastic for seeing how those complex developments shift when you change one variable.
It sounds like the goal is to bridge that gap between the screen and the shop floor.
Exactly. Use the tech to save your sanity, but use your hands to understand the physics. There's no feeling quite like taking a flat, cold piece of steel, giving it a few rolls, a few bends, and watching it snap together into a shape that actually functions. It's like you've tricked the universe into making something solid out of nothing.
Well, just try to keep the cat off the workbench next time you're tricking the universe.
The cat has been banned from the copper projects. That was a hard-learned lesson, but that's the beauty of it. Every scrap piece in my bin is just a lesson I haven't quite finished yet.
I think that's a perfect place to leave it. Whether you're using a compass or a computer, just make sure you leave enough meat for the fold.
Well said. Now I've got a piece of zinc that's calling my name, and this time, the true length is actually going to stay true.